684. We've got higher tier 2017 paper for core physics. So it's probably going to be in two parts, this one. I'll try and get through it. Here's your formula sheet. Okay, first question. It was all about energy savings and this, that and the other. So first thing to recognise that our power is in watts and our time is in minutes. So that's probably going to need converting. It says use an equation from page 2 to calculate the cost. So anytime you do with cost, it's going to be this one unit used. Now note this is a kilowatt hour, still energy. So it's kind of the same formula as this. Look, energy transferred equals power times time, because it's power times time, but this time is kilowatt hours. Therefore, we need to be in kilowatts. We need to be in hours. And then we can use that one then. So I think it was a 4-mark question, which, yeah, it was. So there's going to be equations with an S on and 4 marks, 2 equations. So the first thing we need to do is to convert this into kilowatts. So be smart, mate, stop being dumb. If I'm going from small to big, I need to divide by 1,000. If I'm going from big to small, I'm going to multiply, but I'm going from small to big here, so I need to divide by 1,000. So 500 divided by 1,000 becomes 0.5. And then your wash time in minutes, well, 90 minutes here is 1.5 hours. So this is 1 hour, this is 2 hours. Which is why I've done 0.5 times 1.5 there for when it was at 40 degrees. I got that from the question there. So that comes out to be 0.75 kilowatt hours. Then the cost is easy then, because I just use my units I just calculated by the price of the per unit, and that's going to give me 12 pence. This was a beast, considering it was the second sort of question on the paper for 3 marks. It's total numeracy question. So it's just saying. Well, I'll read the question. The Energy Saving Trust suggests that washing clothes at 30 degrees Celsius reduces the energy by at least 40% compared with washing higher temperatures. So I've just got to pick a higher temperature than 30 degrees Celsius, which is 40. And they reckon it's going to reduce by 30%. So let's check it out. So I know my kilowatt hours there, my units was 0.75. So I'm going to recalculate that. I just need to calculate my energy or my units at 30 degrees to compare them. So I've done 0.5 because that's the power, 500 watts, times 1 because it was 60 minutes, 1 hour is going to give me 0.5. Now I know these two values, I can see, I can calculate the percentage difference between the two. Now they think it's going to be 40%. Let's find out. So first of all, we've got to find the difference between these two. So 0.75 minus 0.5 is going to give me 0.25. And now I divide the difference by the biggest value. Now I know Wooly would have a go at me for that because, you know, you don't know what you're comparing. But it's always going to be the biggest value on the bottom because you're getting a percentage. So 0.25 is going to be my difference. And then 0.75 was my biggest value. And when I times that by 100, it comes out to 33% is the difference between those. Well, they said it was 40%, so they are wrong. So it's incorrect. So 33% is less than 40%, so the claim is incorrect. But what a beast for a second question. I'll just keep that at a second yet because I don't know what's coming. Washing the clothes at 30 degrees Celsius saves money on a household bills. Explain why reducing energy consumption also helps the environment. This is one of those questions that's going to crop up, and we need to know that less energy means that less energy generated by power stations. Therefore, when power stations are generating less energy, they're burning less fuel, so less CO2 and SO2 emissions, so less carbon dioxide, sulfur dioxide. So if there's less emissions, then there's less contribution towards global warming, and therefore greenhouse effects, so better for our environment. State which wire the fuse must be connected to. The fuse is always connected to the live wire. And from that, if you were asked to label these wires, does it show a fuse there? It doesn't show a fuse there. But sometimes you'll see these diagrams and they'll put the fuse in there and you'll think, well, how am I expected to know which wire is which? Well, you know that the live wire is going to be connected to the fuse, and the earth wire always runs to the ground. Describe the function of the earth wire is to take current safely to the ground if a fault should develop. And then for your second mark, for example, if a wire or a live wire touches the metal casing of an appliance. For your other mark there. Let's chuck that up there. All part of the same question here, but it says where the voltage is 230 volts, the mean power of the washing machine during a wash is 500 watts. However, when heating, it must be at this maximum, which is 2,400 watts. This householder has 3 fuses, 3, 5 and 13 amps, and they choose a 3 amp. Investigate whether or not this is a suitable choice. So I've got a voltage of 230. I've got a maximum power of 2400, which you can see I wrote 500 first, but you've got to use that maximum one. And then my equation from the front sheet is going to be PVI, which is here. And I need to investigate for current. So I'm going to stick that in a triangle. I'm going to move P up to make I my subject. I equals P over V. So that's 2,400 over 230 is going to be 10.4 amps. So I will need to use a 13 amp because you need to use a fuse just above, rated just above what the flow of the current flow is. So 3 amps is not suitable. Just out of interest there, I do not need to convert this because the only time to deal with kilowatts is when we're dealing with cost of electricity. So this teacher demonstrates water waves in a ripple tank, which is one of your specified practicals. Now, the first thing that strikes me as odd is that they've only got a maximum distance there, but if you know that there are 2 waves there for 3.2 centimeters, and if you're clever, you'll be able to half that for 1 wavelength. So use the information in the diagram to calculate the distance x. Well, x is from peak to peak, so it is 1 wavelength essentially. I mean, you could go and count the boxes. 1, 2, 3, 4, 5, 6, 7, 8 boxes is with 3.2. Then you could divide that by 8 for each centimeter, and then you can say, well, I got 1, 2, 3, 4 boxes there. But knowing that's a wavelength, I only need to divide by 2 because I got 2 waves, so I got a wavelength of 1.6 centimeters. A wave takes 5 seconds to travel 40 centimeters along the surface of the water. Use equations. So we got an S from page 2 and information to calculate the frequency of the wave. So we got 4 marks, 2 equations needed. It's giving me time. Got my time. It's giving me a distance here. Okay, so that's not a wavelength. So I really need to find the speed of the wave in order to use this one. I need the speed. Look. I've got, did it give me a frequency? No, I calculated frequency. I've got a wavelength up here, which is 1.6. I need a speed. And to get speed equals distance over time. I'll show you where that is at the front of your books. It's right at the bottom. Speed equals distance over time. There she is, look. And we're just going to fill out the blanks then. So we got 40 over 5. So we got 40 centimeters over 5, which is 8 centimeters per second. Notice I'm in centimeters here. I haven't converted that to meters because this is also in centimeters. And when you've got matching units, you don't need to do that. Now I've got my speed, I can whack it in the frequency. So frequency, cover my F, is V over lambda. So V over lambda, 8 over 1.6, which is my wavelength, gives me 5 hertz. Oh, this one, this is, well, it's a question, I suppose. You just got to know to draw a line through there and back and put the wave fronts equal distances is that one. So light, the rule is the angle of incidence. So this is our incident ray. In fact, I think I'd lose marks on this because I haven't got an arrow showing. So if I just draw an arrow on there, oh, way off. Let's have a look. There we are. And then an arrow back out. The angle of incidence equals the angle of reflection there. So these wave fronts are going to be identical. Question 3 then. I thought this was nice for 3 marks. We should be knowing how to draw a standard test circuit. Now you've got your Power source, and they'll accept any power source. I've just put a simple cell, but you could have had DC current, you could have had AC, you could have alternating currents, up to you. Your ammeter, which is going to measure current, your filament lamp in there, and then your voltmeter across that filament lamp because it needs to be in parallel, and then you've got your variable resistor, which is going to alter the resistance of the circuit. And remember, if you're asked for, I don't know, four marks on how to gather a series of readings, you would say, I'll set this to maximum. That's not going to allow any current or voltage through. And then I'm going to gradually adjust this, okay? And then I'm going to take readings for voltage and my current with using the ammeter. And probably use V equals IR to calculate my resistance then. But you can see they've got a series of results here. So when it was 0, that was 0. And they've adjusted incrementally for voltage. And voltage tends to be your independent variable here. You're going to go voltage in equal steps and then plot your current against that. Now I'm suspecting you've got a graph, which you have. So the scale was a little bit awkward here because you're dealing with such small values. Sometimes they'll put that in milliamps. So just like a millimeter is a thousandth of a meter, milliamps is just a thousandth of an amp. So don't be scared if that's in milliamps, but this figure will be bigger then. So 0.2 all the way up to 1.2, and then a nice scale on the bottom, and then hopefully you will know to do the curve because it's a filament lamp. So it starts off proportional, and then it starts to, as this increases, as voltage increases, current increases at a decreasing rate there. She concludes that the resistance of the lamp decreases as voltage increases. Explain using calculations whether you agree with this. Well, we could do two calculations to prove this. So I could say if I'm looking for my resistance, I'm gonna from my graph, when the voltage is 2, and I've drawn a line up there, you can see that my current is 0.4. I can also get these from the table as well. And when I do the calculation, 5 ohms, and then I've just chosen a greater value for voltage because she says as voltage increases, resistance is going to decrease, she reckons. But it doesn't look, because when I get those readings from the graph or from the table, resistance is also increasing. So she is wrong.